In this video we're going to look at the Alkane homologous series. Homologous series is the name we give to a family of carbon-based compounds. So compounds in the same homologous series will have similar chemical and physical properties. They'll have the same general formula. The only difference between them really is the number of carbons in the form the backbone, the spine of the compound. So they differ in formula by a CH2 group, a carbon and two hydrogens. But they do have the same functional group. That's the bit that makes them unique. So we're going to look at the Alkane homologous series. Now the Alkane homologous series is found in crude oil. That's our source of alkanes. And crude oil is a mixture of different alkanes with a different number of carbons in the chain. Now these alkanes are hydrocarbons. This is the first definition we need. Hydrocarbon compounds. And these contain only carbon and hydrogen atoms. Okay, it's an examiner's favourite question, but a hydrocarbon contains only carbon and hydrogen atoms. You can have different homologous series that are not hydrocarbons. They might contain something like oxygen or chlorine or something, but the alkanes are hydrocarbons. So this table shows the first four members of the Alkane homologous series, and we're going to put our formulas and draw diagrams of their structures. To do that, we need to know that carbon always forms four bonds. How many bonds does carbon form? Four. How many bonds does hydrogen form? Well, hydrogen forms one. So the first member of the Alkane homologous series is methane. Okay, now we have a way of counting the number of carbons in these carbon-based compounds. We have a new numbering system, a different language for numbering. So chemists don't call one carbon, they call one carbon meth. Let's just write that down here, it might be useful to us. So meth means one carbon. Okay, so our formula is going to be C, and carbon forms four bonds, so it's going to be CH4, and our structural diagram is going to look like this: carbon with four lines coming out. The lines are, of course, covalent bonds. A covalent bond is a shared pair of electrons, and our structure is going to look like that. Now, our next formula of our second member of the Alkane homologous series is ethane. So our word for two carbons is eth. Okay, two carbons. So that's going to be C2. Let's put our C2 there. Carbon forms the backbone of the compound, so it looks like that. Now for every carbon, there's a hydrogen above and below it. So to find the number of hydrogens, we simply double the number of carbons, but there's also a carbon on both ends. So it looks a bit like this. Okay, so we double the number of carbons, 4, to get the number of hydrogens, and we add two hydrogens on the end, so 6. So C2H6, and this gives us can give us a general formula for these compounds. I suppose we can write this out now. A general formula is a mathematical formula that says if we know the number of carbons, so let's use the letter N to mean any number of carbons, we can calculate the number of hydrogens by going 2 times N or 2N. I'll do 2 times N like that. It's sometimes written 2N without the multiply because in maths, if there's nothing between them, it means multiply, but I just think it's clearer in chemistry like that to write 2 times N. Okay, so to get a number of, if we know the number of carbons, we double it to get the number of hydrogens, 2 times N, but we have to add those 2 on the end as well, so plus 2. So that's C2 doubled 4 plus 2, 6. Okay, propane is our next member of the homologous series. So prop is our chemical language for 3 carbons. So that's going to be C3. So if we double 3, we get 6. Plus 2 is 8, so it's going to be H8. So C3, 2 times 3 is 6, plus 2 is 8, tells us the number of hydrogens. Let's draw it out and we can see that. 1, 2, 3 carbons. Double it, hydrogens above and below every carbon. So that's 6 hydrogens I'm putting around those 3 carbons. And of course we've got 1 on either end, so that's 7 there. And that one is 8 there, that's propane. Okay, and our last member of this homologous series is going to be butane. So bute, but you might want to write it out, but we pronounce it bute, is going to be 4 carbons. So bute is the chemical language for 4 carbons, so C4. Okay, so double 4, 2 times 4 is 8, plus 2 is 10, so that's going to be H10. And it's going to be 1, 2, 3, 4 carbons in a row. Double it to get the number of hydrogens above and below each carbon, so that's 8. And we're going to add 2 on the end as well. 9, 10. Okay, so there's our first 4 members of the alkane homologous series. Are these compounds ionic or covalent? They are covalent because, of course, carbon is a non-metal, hydrogen is a non-metal, and a covalent bond is a shared pair of electrons. So that's the alkane homologous series. This next page here, we've got a bit of revision from year 10 at the top, so I'm going to skip that out right now just to keep unique stuff in these videos. Let's have a quick look down the bottom here. When long-chain hydrocarbons are cracked. So the long-chain hydrocarbons from oil, long-chain hydrocarbons, what we mean by a long-chain hydrocarbon is an alkane. Okay? So these members of the alkane family we've just looked at here, these are all short chains. Okay, when I say a long chain, I'm meaning minimum really 10 carbons, I suppose, but really 20 or 30 carbons in that chain. So when we say cracked, what it basically means we heat the molecule up and it wobbles, and we heat it a bit more and it wobbles a bit more, and suddenly it wobbles so much that a couple of carbons crack off the end of the chain, break off the end of the chain. So when long chain hydrocarbons are cracked, shorter chain alkanes and alkenes are produced. So we've got a different homologous series here. Alkenes, we started with alkanes, that's from crude oil. Okay, alkanes from oil, crude oil. Okay, alkenes from cracking. That's important. So we do not get alkenes in crude oil, we get alkenes from cracking alkanes. Now that's confusing because there's only 1 letter difference between the two, but it's important. So when long chain hydrocarbons are cracked, shorter chain alkanes and alkenes are produced. Complete the following equation showing examples of different cracking reactions. Well, once you understand the first rule of chemistry, these could not be easier. Okay, the first rule of chemistry is what you start with, you must finish with. You cannot make atoms or create or destroy atoms in chemical equations. So on the left-hand side of the arrow here, we've got 14 carbons. On the right-hand side of the arrow, I've got 12 carbons, so there's 2 left over. So that molecule there that's produced as well must have 2 carbons. 12 plus 2 is 14. Likewise, the hydrogens. 30 hydrogens on the left, so far only 26 on the right, so it has to be C2H4. Next one, C15H32. I've got 15 carbons on the left, 12 on the right, so there must be another 3 there. So 12 and 3 is 15. It's 15 on the right, 15 on the left. 32 hydrogens on the left, 26 on the right. What's that? There's 6 short then, isn't there? 32 minus 26 is 6, so H6. 6, and that 26 makes 32, and there's 32 there. Going back the other way, it's just as straightforward, really. Okay, so you've got 10 carbons on the right, 13 carbons on the right, so it's going to have to be C13 there. Yeah, and you can work out the hydrogens on your own. This third example here, 16 carbons there, we've got 11 there, plus 3 is 14, so there's another couple kicking around, so you can fill that one in as well. The important thing from these cracking equations, is you realise alkenes, okay, alkenes are formed from cracking. So we've just got a quick fill in the blanks here. I've been using this fill in the blanks with classes for absolutely years. I just think it's quite good, so let's quickly have a read through it. Alkanes and alkenes are 2 different homologous series that are both hydrocarbons, because they're both made from hydrogen and carbon only. Okay, all the other homologous series we're going to look at in the triple science unit are not hydrocarbons because they will contain oxygen. Okay, but alkanes and alkenes are hydrocarbons because they contain only hydrogen and carbon. A hydrocarbon is a compound or a molecule, you can say compound if you want, made of carbon and hydrogen, okay, only. Let's just square off that box there. That is really important, okay? Only hydrogen and carbon. Alkanes are found, we've said this already, crude oil. That's why I quite like this fill in the blanks, it's a nice summary. Alkanes are found in crude oil, and alkenes, so notice the difference, A and E, and alkenes are produced when long chain alkanes are cracked. We heat them up and they wobble apart, they crack apart. Okay, and we end up with a shorter chain alkane and an alkene. Alkanes have carbon-to-carbon single bonds. Okay, let's just go back. So those alkanes we drew a moment ago. In the middle of all of these, there's carbon-to-carbon single bonds. Okay, every other bond around the carbon has a hydrogen on it. Okay, there's carbon-to-carbon single bonds. Alkanes have carbon-to-carbon single bonds and are known as saturated. So we call alkanes saturated. Okay, Why? Because they have carbon-to-carbon single bonds. Okay, whereas alkenes have carbon-to-carbon double bonds. There's a difference. And we'll look at some alkene diagrams in a moment and you can see the difference. So an alkene has a carbon-to-carbon double bond and are known as unsaturated because they have a carbon-to-carbon double bond. The double bond is a reactive site. Okay, what that means is you can react an alkene with something else and that double bond will open up and react with those other things. The double bond is a reactive site. Alkenes are therefore more reactive because there's no double bond in the alkanes. Alkenes are therefore more reactive than the corresponding member of the alkane family. And that helps us with a test for alkenes. So first, here's our alkene homologous series. Now you can't have methane because you need a carbon-to-carbon double bond, so you need at least 2 carbons. So our word for 2 carbons was eth, so this is ethene, so it's going to be C2. Let's draw out our carbon-to-carbon double bond. Notice the difference, okay, between ethane and ethene. Here is ethane, single bond. Okay, here is ethene, double bond. Okay, now carbon can form 4 bonds. This one's already got 2. 1, 2, so 3, 4. Okay, this carbon's already got 2 bonds. 1, 2, 3, 4. So we've got less hydrogens around this one, okay, because one of those bonds is between the carbons. So 2 carbons, 4 hydrogens. Okay, so our general formula for alkenes, okay, is going to be Cn, where n is any number, and we simply double it 2 times n to get the number of hydrogens. So C2H4. Propene, it's only got 1 double bond, so it's C3. Okay, some students sometimes draw it with 2. We only draw it with 1 double bond. I'm going to do it like that, but you can put the double bond there and a single bond there because it's just like looking at it from behind, isn't it? If you do it the other way around, you're going to turn the molecule over and the double bond flips place, but the molecule is still identical. Okay. Now, the standard mistake here is to put too many hydrogens around the carbon, so count the bonds really carefully. This carbon's got 2 bonds, 1, 2, so it needs 2 more. 3, 4. This carbon has got 1 bond, so it needs 3 more. 1, 2, 3. Now this is the place people make mistakes because look, it already has got 1, 2, 3 bonds. It only needs 1 more. So many students put a 5th bond around that, and it's wrong. And for that reason, this is an examiner's favourite question. Draw propene. Okay. So that's C3. 3 doubled is 6. C3H6. Butanene now, C4H8. You may say, what on earth's butanene? Okay. Well, this 1 here tells us where the double bond is. In other words, it's on the first carbon. 1, 2. That double bond is on the first carbon between the first and second carbons. So it's got 4 carbons, and butanene means the double bond is there. So again, let's get the hydrogens really correct by counting the number of bonds around the carbons. So this carbon's got 1 bond, 2, 3, 4. This carbon's got 2 bonds, 1, 2. This carbon's got 1, 2, 3 bonds, so it only needs 1 more. Okay, and this carbon's got 2 bonds, so it needs 2 more. There we go. On every bond, draw hydrogen. Well, butanene, this time C4H8 again, so it's still butene. So it's still 4, but is 4 carbons, ene is an alkene, so it's this general formula. C4H2 times 4 is 8, but this time this double bond is on the second carbon, so 1, 2 carbons, there's our double bond now between the second and third carbon. There we go. And again, we need to count these really carefully to get the hydrogens correctly drawn. So 1 bond around that, 1, 2, 3 more, so that's 4. 3 bonds around that carbon already, so only 1 more. Okay, let's start putting some hydrogens on these as we go this time. 1, 2, 3 bonds around this carbon, so only 1 there. And this carbon now, 1, 2, 3, 4 bonds around this carbon. Just where I've been sketching, it almost looks as if I've done a double bond there. That's a single bond. Okay. What is the functional group of the alkene homologous series? The functional group is the unique thing about this hydrocarbon. The unique thing about this hydrocarbon homologous series is the carbon-to-carbon double bond, the double bond. And that is an introduction to alkanes and alkenes.